Hello, my name is Nelik, and today we're doing a little MacGyver special recording of the testing that will accompany the article published in Pumps and Systems magazine that you can look up. The article would be in September issue of 2021. And that article talks about vibrations and noise in pumps. In order to understand the relationship between vibrations and noise, the article addresses that the noise essentially is manifestation of something wrong, depending on the volume, on the degree of noise, degree of the vibrations producing the noise, and some methods that can be applied to reduce the vibrations and sometimes reduce noise. The article discusses that for pumps, usually vibration is an issue, and there are the specifications published. Hydraulic Institute has specifications, ANSI, ISO specification, API specification, and many other ones. They talk about allowable levels of vibrations. If pumps operate below allowable at lower levels established from experience, to achieve a long life. And what's long life, of course, subject to interpretation, but it's certainly not 2 or 3 years. When people talk about good reliability and long life of equipment, they talk about 25, 30 years running with occasional maintenance and adjustments, but basically nothing catastrophic supposed to happen in the times of less than 25, 30 years. The noise by itself, not really an issue. The noise doesn't really ruin equipment normally. The concern about that is environmental. OSHA standards, usually we allow 85 dBA, decibels A scale, above which it's detrimental to human hearing. But if majority of pumps, 90% of pumps and motors are installed in areas where not really that close to proximity to human hearing, and people at the plants, as we all know, usually wear the earplugs or earphones. But the noise is also a manifestation of something is happening with the equipment, and it's accepted fact that rotating machinery generates noise, and as long as noise and vibrations that causing that noise are below the low levels, everything is fine. But sometimes the situation with pumps, sometimes actually smaller pumps, not necessarily very huge ones, are installed in a system like a cooling modules of the airplane hydraulic system, or something that is relatively compact, and it has a lot of filters, gauges, relays, and so forth, small tubing, so that even low-level vibrations, way below the specifications, can ultimately cause a natural frequency fatigue of some components. Broken gauges, we all saw at the plants walking by the pump or the pipe and looking at the gauge with a needle laying down there, broken off the gauge. So that can happen. So the noise could be not only indication that something needs to be done to protect our hearing, but also something needs to be done to protect equipment from failure. To isolate equipment, our article in Pumps and Systems discusses, there's various methods employed and deployed. Isolations, vibration pads isolations, expansion joints, dock houses to enclose equipment so that to minimize the transmission of the mechanical vibrations and noise also with that from spreading out through the metal frames, through the air, to the environment. Those dog houses, enclosures, are kind of the black art a little bit. And today, people do about trial and error. What system works best? So acoustic enclosures, you probably find many articles even on internet for local suppliers, acoustic enclosures. The question is, how effective are they? How thick the walls need to be? What type of materials to be used? How environmentally friendly? Are they dangerous? Asbestos, probably might be good isolation of thermals, maybe even vibration and noise, but not good nowadays from the OSHA standpoint, from an environmental standpoint. So here we try to do a simplified experiment to get to the basics, to the fundamentals of the noise, of equipment that actually muffles the noise. So we're not going to talk about much about vibrations today in this video, but actually talk about the noise and sound reduction. Behind me here in our laboratory in Israel, we have several offices in US, in the Middle East, and this is an office in Israel where we do pump research in energy, efficiency improvements, specialty designs, rapid prototyping, and this fits perfectly into, as I call it, MacGyver special fundamentals to understand it. How thick equipment, how thick the material needs to be, how dense or thick it needs to be, how solid or flexible. Is it a soft, like a sponge-like material that would absorb noise better? Or is it a hard rock-like metal or plastic surface that bounces the noise away? Can we absorb the noise or can we bounce it away? But one way or another, we want to somehow isolate the noise from the environment. Between the noise and the environment must be some sort of wall. What is it wall should be made from? So here, we have several materials that I'll show you in a moment, but we have a noise generator, just a bullhorn, then we can turn, and then we have a noise dB meters. You can read dBAs or dBCs over here. So you can see as I speak, it registers the dBA level. And what we will do, we will look at the following equipment. So I'm going to walk around and show you what we have here. We will use a simple cardboard. We try just a regular off-the-shelf plastic plate, about 4 millimeters plastic plate. Another kitchen plate that you all have in your kitchens. Then just a small metal plate. Next to that, kind of moving to the left, there's a piece of our carpet. Then thick couch pillow. Then the pillows for the chairs. Then the pillows, bed pillows over here. Then the brick, just regular brick, about 60 millimeters brick. Styrofoams for industrial application, industrial insulation. Here are styrofoams of different thicknesses. A doghouse, a sample, a very small doghouse, cardboard enclosed with styrofoam. Just a small cardboard box to see how effective that is against the noise. And then we have here tabulations grouped in A, B, and C. We have pre-done it already, the test, and filled the numbers. But I will run this test for you one more time to get you a feel for, first, we'll see the noise when there is nothing running in the room, quiet. Then what happens when we have just air conditioner running? Just already looking at these values, 40 decibels, absolute nothing happening, just a background noise of the cosmos, I guess. And then with air conditioner running, the noise goes to 50 decibels, 10 decibels change. Then we'll turn the horn to about 91 to 95 decibels. And then with horn running, we'll try different materials, 4 millimeters cardboard, plexiglass, plastic, carpets, multiple layers of carpets. Then the horn will be 1 meter away from the wall. And the way we'll be doing it simply, we'll put the horn directly, kind of like it's shown here, directly on the material. If it's slightly away, take a look at this. Only if I completely touch the surface, it really becomes effective. So in reality, it's not exactly how the noise is not in direct contact with isolation. But for simulation, for comparative purposes, that will be apples to apples test. The tabulation A
will show the equipment that you get in your home: plexiglass, cardboard, pillows. About 14 different situations we'll study. Then from number 15 to 25, these are more industrial ones. The foams, the sound dampeners that you can find like this, that you can use in recording studios, for example, different shapes. And then we'll also do 2 dog houses. Then we'll make a plot of which equipment works better, lower reduction, and that's mentioned in the article. So let me set the recording on the table, and let's actually do a little testing. So the first one, with nothing running in the room. I just went and turned off the air conditioner. About 40 decibels, dBA. Turn the air conditioner back on, gets a little bit cooler in the summer. I just turn the air conditioner on. Background noise goes to a little bit below 50. As I speak, by the way, my voice in this roughly a meter away from the receiver gets about maybe up to 80, 75 to 80 decibels, just a loud talk. So the first test I will do is so horn only. So I'm running the horn. The meter is registering about 91 to 95 decibels, and the purpose of the video is actually for you to feel, to hear the sound. Tabulation you can see in the article and examine it later, but it's about 91 to 95 decibels. Why is it 91? Why does it rain? Because the horn goes like this. It's sort of higher and lower, so there's this variation of the sound. So between 91 and the meter picks it up, so 91 to 95 decibels. The next one we'll try 4 millimeters cardboard, just a regular cardboard, and you'll see a reduction. It will go to about 82 to 84 decibels. Listen. Not too effective, but 82. 95 to 82, 84, that's about 10 decibels reduction, just with the regular cardboard, 4 millimeters, corrugated cardboard, just a regular box. If we next try a plexiglass, it's just a door from the cabinet. Try this. Only completely with a pull worm, and the simulation doing this way, putting the bullhorn exactly directly on the surface, is that the insulating rim makes sure that very little sound actually escapes from outside. Some dust goes around it. We can't help that. To make it really perfect test, entire box will have to be made from the plexiglass, from material, and the noise generations will have to be coming out from inside that box. But that's more complicated test, and just for simplicity, we'll say it's not perfect, but it gives you comparable difference from one material to another. So you can see here, we're going from this noise to very low noise. That value recorded for plexiglass is about 60 to 63 decibels. Let's take another piece. We'll take a plexiglass, just a little vegetable preparer for a kitchen that we can prepare salad. Almost the same effectiveness as another plastic. It's a little bit thicker, it's different material, and I don't even specify here for purpose of our test exactly what type of plexiglass, what type of chemical compositions. At this point, we're not interested in to know exact number. We want to get a little bit of order of magnitude, if you will. So that board gets us to about 62 to 67 dB, and I'm also plotting it on the chart. The next one is a metal chip. So what happens when we take metal chip? Well, pretty significant reduction, just very thin, 1 millimeter thick metal sheet, but reduces the decibels from 95 to about 66 to 72. So it's about 20 decibels reduction. So the entire house was metal, not taking into account the resonance that metal might be resonating, but just the ability to, if that whole room was in 1 millimeter metal, and I would be generating this 95 dBA sound, it probably would keep it from coming out of the room, assuming that I will not have a box in resonance with the frequency that's emitting. The next one is a regular piece of carpet. So take a piece of carpet, about 8 millimeters carpet with a little vinyl backing, put that against it. Not much. And if I take 4 pieces of carpet, throw them together, doesn't seem to be doing that much better, even with 4 pieces. So, 1 piece of carpet was 78 to 79 decibels, and then 71 to 78 decibels, just a little bit less with the 4 pieces. What if I take a regular couch pillow? Nice 200 millimeters, 20 centimeters pillow. Muffled is pretty good. So it can be either very hard, thin, hard plastic, or thick, soft, fluffy material like pillows. That pillow reduced the sound from 95 to 63. So it's 30 decibels. What if you take a different pillow, which is a chair pillow? Pretty good reduction, about not as good as the thicker pillow. That's only 78 decibels now. But if I take 2 pillows together, something interesting happens. 2 pillows together are still thinner than the big pillow, but the sound is significantly more muffled. 1 pillow dropped it to 78, and 2 to 63. So it's another 15 decibels. The second pillow added another 15 decibels reduction. That pillow, let's take this. You can buy these pillows at the regular store, furniture store, I guess. It's called Unica Beauty Pillows. If I use that, it's about 50, 60 millimeters thick pillow. Noise, 58 to 60. 2 pillows together, 57, 58. Interesting, the 1 pillow does most of the job. The second pillow, for some reason, doesn't add very much. Perhaps, because remember, air-conditioned noise now is 50 decibels. If we drop it to 58, there's not much more you can really do. 58 becomes to 51, so we will finding, generally speaking, proportionally doubling the layer of insulation doesn't double the drop in decibels. It gets, if the first one does 100% of the job, the second gets you maybe another 20% or maybe 10%. So by adding layers doesn't help very much. But if you start stacking layers and putting different materials, combination of materials in between, perhaps have a different story. We're not covering in this video, but you can think about doing something like that, like your triple windows that you have for sound and the thermal reductions for the temperature control. Those windows have to have space between the glass sheets. That space ideally should not have been filled with air, vacuum filled. evacuated air, and even if it's not evacuated but air still remains there, the gap might be not small but quite big, maybe 10, 15 centimeters to become effective. So the good triple glass window to drop the sound coming into your room, into your bedroom, probably have to be that thick. Sometimes it's not practical to make windows that thickness, but anything thinner than that wouldn't really get you that much improvement in a comfort for your. You would think, maybe somebody who sells sound windows will tell you, I have a just triple window, 3 layers of glass. It will help from a temperature control standpoint, but it will not help very much from the sound. For the sound, you need a multiple layers separated by the huge distances of air or some material, or very strong solid material like we just did here, plastic, metal, or something like that. The next one, so that is our readily available table A materials you can buy at the store across the street. Now let's get a little bit more industrial. If we take a 15 millimeter white foam, you can see it didn't do that great actually, that foam. It dropped to 88 decibels. So it's about 10 decibels reduction. Now what happens if I take 2 of them together? Doesn't make that much difference. So 85 went down to 78 to 80, another 3 or 4 decibels we reduced. What if I put 6 of them together? 6 panels. You can still hear the sound pretty strongly coming out of there, and it's 78. So we went from 85, let's say, to 80. Another 5 decibels, roughly a decibel reduction per centimeter. Roughly, you can go every centimeter gets you another 1 decibel. So 10 centimeters, maybe 10 decibels. So the layer will have to be quite thick to become effective, which is many times simply not practical. You want to have layers of insulation relatively thin, perhaps 50 millimeters, 5 centimeters, 20 millimeters, something relatively small and light and easy to handle. Another panel we will try. This will be another type of styrofoam, just a little bit different. You can hear the sound roughly the same, and decibels for that styrofoam 81 to 82. I have another piece which is multi-layered styrofoam. Hear the sound? The multi-layered styrofoam brought us 78 to 83, let's call it 80 decibels. Very similar to the other styrofoam. So the lesson we already learned, the styrofoams, almost independent how thick they are, even very thick multi-layers, don't do very well against sound reduction. They dropped it from 95 maybe to 80, maybe 15 decibels in the extreme case when I have many, many layers together. 1 decibel per centimeter could be probably a rule of thumb from what we're finding here. The next one, we'll try acoustic foam. This acoustic foam, you see it many times in recording studios. They are really not designed to keep the sound from coming through it. They're designed to spread the sound and make it nice sounding sound in the recording studio. Look at this. Essentially no reduction. If I talk to styrofoam, my voice doesn't spread through the room so easily. So it kind of cushions the sound, rectifies the quality of the sound, but doesn't prevent it from coming through. Even if I take multiple layers, look at this, 6 layers, and run them together. You can see it didn't help very much. On my table here, that styrofoam was 8 layers. 87 to 90 decibels. 5 decibels reductions only with the 6 layers. Again, a decibel per layer. And each one is roughly a centimeter, maybe centimeter and a half in thickness. Another type of styrofoam. Also, you see it commonly in recording studios. Let's try this. Another type, different design. Try this. You hear not much difference. Even if we take 18 pieces together, let's make this a little experiment here. You can still hear the horn pretty strongly, and that's about 75 to 82, let's call it 80 decibels. So you went from 95 to 80, 15 decibel reductions with 18 layers. So a layer, a decibel per layer. This is a little bit thicker than the other ones, but it's similar. So overall, maybe a 1 decibel per centimeter roughly can still be applied regardless what type of design. And I tried it this way and with the dimples the opposite way. Doesn't make that much of a difference. From spreading noise, perhaps it does, but from keeping it from going through, it doesn't help. So let's take the extreme case. Let's say we have a concrete block. We have a concrete block here, brick, 60 millimeters, 6 centimeters. Brick actually dropped it to 59 to, let's say, 60 decibels. That's about 35 decibels reduction. So brick, obviously, when you're in the room with no windows, you usually don't hear very much from outside. Sometimes when the neighbors are talking, you can hear them even through a brick wall. But it's very muffled sound. So brick is very effective, but of course, it's not very practical from the standpoint it's heavy. To construct something for your home, to close the window with a brick, you will not have a window. You block the window. There are also materials that we haven't tested. They're called mass-loaded vinyl, MLV, mass-loaded vinyl. There are companies, a company in New York, I believe, they make them. It's a transparent. You can make a panel, put it against. It's thin, maybe 10 millimeters, 20 millimeters. Maybe 15 millimeters, not exactly sure exactly on the thickness, but it's relatively easy to handle. You can lift it yourself, put it against a window, make additional frame, if you will. It's transparent, so you can use it not only during the night, but during the day. And you drop the decibels, probably about 15 decibels, maybe 17 decibels, but not really by 30. If you will double those together, you get another 5 decibels, but as I mentioned earlier, you can, as you saw here, adding more layers doesn't really help very much, except there are some exceptions. In case of these 2 pillows, there was a pronounced effect. 2 pillows together, 1 pillow dropped it by 15 decibels, and 2 pillows dropped it by another, so almost doubling reduction. That was one interesting, pleasant exception to the rule. Well, let's try a little doghouse. I have here, let's say we constructed a little cardboard doghouse, simplified case, without enclosures. Just let's see how effective that is. Small doghouse. I'm not putting it inside, look, because I need to have a contact with the wall for consistency of testing. So here, about 80 decibels, 15 dB reduction. And if I make something a little bit more sophisticated, cardboard lined with this white styrofoam panel, and you already saw in the previous testing that styrofoam doesn't do very well. So here, that box about 74 decibels, which is about 20 dB reduction. 20 dB reduction. Again, what a little bit inconsistent with our test, why it makes it not exactly fully valid, is that when we put the horn to the wall, we're still not isolating the sound coming from the horn outside. Our ears registering sound not only going through the wall, but also through the air around it. In order, I mentioned in the beginning of the video, in order to make it valid, we'll have to make an entire enclosure of this material, keep the source inside, something like this, fully enclose it, and then test it and see how well a full enclosure will take care of it. But on the other hand, if you make this material, if you make from either of these materials, you make like a frame for your window. Let's have a window at home, 1 meter wide, 1.7 meters long, and if you take one of the good materials, let's say pillows we talked about, and put them together and create a new window, maybe adding another frame that you can close at night when you don't need the light, or open during the day, so during the day, if there's noise outside, that's not going to help you, but at night, if you want to cut out the street noise or people talking outside noise and waking you up, you don't care for the light, you can do that, and you can add this, close it, and that will be pretty effective, because the noise, as long as there's no spaces coming around the frame into your room, that will be very similar to what we have here when we're essentially putting the surface of the horn right against the surface of the material we're testing to see if nothing comes through that. That can be an interesting debate about what I just mentioned. And those of you who perhaps have some background in acoustics, please challenge me and let me know what you think. Well, let's come take a look at the tabulations. Now, I plotted this data on the table. I'll pick up the recorder. We'll work with this. So again, this is tabulation. You're welcome to make a copy. That's a series A from readily available store materials. That's table number B, which is more industrial styrofoam, and below table C for the doghouse design. And here's a tabulation graph, 27 cases that we tested here. And this is dBA from 30, 40, 50, 60, 70, 80, 90, 100 dBA. And you can see that I put the red ones, I circled number 5 material, number 10, and number 13. This, and this. Number 13 and 14 were most effective. What are those 13 and 14? Everything else, really, like for example, number 3, remember number 3 didn't change very much. And well, of course, nothing to change. That's a base running, 95 dB. And then if you go to number 4, it's about 84 dB, not very much reduction. And number 4 was 4 millimeters cardboard. But when you go to 5, which was 4 millimeters plexiglass, you went to 60 to 63. Or 200 centimeters couch pillow, 61 to 63. Or 120 centimeters bed pillow. In other words, this pillow, all this pillow, all this plastic plate essentially became the winners from all these materials we tested. You can see, interesting, from 13 to 14, from this point to point, that's 13 to 14. 13 is one pillow, white pillow. 2 of them together don't change things anymore very much. So that's a winning combination. So what type of material is it? It is soft, and yet this foam is a memory foam. It's a memory foam. They make pillows, advertises pillows to comply to the contours of your head and the neck. So if you squeeze it, it retains the shape. See, it's not very easily bounces back. It's a nice squishy foam. So it's soft, it's squishy, and yet it's dense enough to absorb the sound. It doesn't bounce the sound as much, it's absorbed. Perhaps some of this bounces back, some gets absorbed. That's probably a project study on its own. But this is what we're finding. So that's interesting video. Hope you'll enjoy. You can then try this with what you have. Or here's a little end suction pump that you can construct make a dog houses, perhaps making from those pillows, and put it over
over the pump in some fashion. Obviously, it's very rudimental way I did it. Need to cut out properly openings, the connections to the motor, and so forth. But that will be a very interesting test to do, to take these pillows, put them inside the box, and see how the generation sound will be dropped from fully enclosed enclosure. So, with that, I will finish the video. You'll find it nice, entertaining, simple things. Like I said, my guy was special. You have to think simple before you go complexities of unobtainable. Try to see what can you do to really solve your problem. And hopefully that little test accompanying with article on pumps and systems and a September issue 2021. If you don't find it for some reason, give me a call. You can always find me. Just send me the email. My email is drpump@pumpingmachinery.com. It's DRPUMP, drpump@pumpingmachinery.com. My website is www.pumpingmachinery.com. Shoot me the email. Any questions? I'd like to hear from you. Perhaps find some inconsistencies with our testing, maybe some ideas to enhance the testing, how to make it maybe not complicated, simple, and yet more telling. Perhaps to construct the entire room with a source generator, to do it right, so to speak. But you can see, you can accomplish a lot. I think with these little testings, even though the sound generator right against the material, and still some of the sound goes around the environment, it's still for comparable purposes to without material might be a good first check. You can take your horn generator to a supplier and test material right there. Even if you don't have a sound meter, just putting against it and listening with your ear already gets you roughly how effective that is. And once you determine from 20 or 30 potential candidates material roughly what you want, then you can go ahead and construct a little proper enclosure with that material and saving your time and effort to make it much more elaborated, involved projects, which ultimately will not get you that much more extra information that you need to make your pumps quiet. That's not, again, I mentioned, it's not that you will make it vibrate less. We're only addressing the sound. To choke down on vibration, you have to do other things. Put dampeners. Some of these materials put under the feet of the pump will not work the same way they work against the noise reduction. They have to have different characteristics. They have to have some the stiffness and mass and bounciness, springiness must be of different behaviors comparing to its effect on the noise. And yet, enough information in this little video for you to become interested and perhaps practically motivated to make something happen. So let me know how it worked for you. The best answers or any answers we will try to address and maybe publish also. If you have a little video, send it to. We'll publish that and maybe other people will benefit with your findings. Hope you found it useful. Until then, keep on pumping.